Hi everybody, I'm Serkan. Thanks for the invitation. I've already presented this in my thesis, so it wasn't too much work, and it's good to be here. So today I'll be talking about video-based music generation. It's a big problem with multiple components. I start with a motivating example of why videos need music. I mean, the answer might be obvious to you, but then I'll play two clips from a documentary called Koyani Katsi, which is like an indie film. It doesn't have any plot, it just has scenes. It's kind of like Baraka, but Baraka is kind of newer, so this is the old version. And the music is composed by Philip Glass. So the music and the video really comes together in this movie. And to answer the question why videos need music, it's to increase the user engagement. So, you know, cinema or video is one art form, and you can kind of enhance its effects using another art form, which is music. And these two examples will show two different things. The first one will show you the importance of temporal synchronization between the music and the video. So what I would like to ask you to pay attention is the scene cuts, scene boundaries when a scene changes, and how the melodic segments align with those scene cuts. So let's hear the first one. Let's see. As you can see, as the scene cuts change, the musical boundaries kind of align to it. And the second one shows the importance of matching emotions between video and music to enhance the emotions even further. So now after answering this question, why videos need music, we ask the other question, why do we need automatic video-based music generation? The answer is there are tons of videos uploaded to YouTube every day. Now we have a new profession called content creators. So these people need music to enhance their videos. Their options are to either buy the music, which is costly, compose the music themselves or hire the musicians, which is time-consuming and costly, or to use royalty-free music, which is also time-consuming to find it, but it may not fit the video as well. So if we were to have an automatic music generator, all this process would be free, fast, and it would be aligned to the video, meaning that it would fit the video or whatever music that's been created by this model, if the model is good enough. So before we begin, let's talk about the two different music formats. So we have audio and MIDI. So with audio, as you can see on the left-hand side, you have this waveform, but then when you zoom into this waveform, you see that you have these samples at each milliseconds and even shorter than that. So that's why, like, when you look into the audio, you have 1 million samples per minute, and this is at 16 kilohertz. So this is a lot of data for just 1 minute. So it's very difficult to model it using neural networks. Only recent non-commercial models can generate up to 1 minute, and the music is usually longer than 1 minute. There's Tuno, you know, like, and then there's all other stuff, but these are commercial models, these are proprietary. We don't know what's happening in the background, we don't know their data sets, so that's another thing. So it's not academic pursuit. And the second problem is the audio file is not editable in a way that you cannot change the composition of an audio because you have the final audio. Whereas MIDI on the right-hand side, MIDI is a symbolic format. We also call it symbolic music. What you have is you have the notes of a piano at certain time points. So you don't have the audio that these notes results from, but you have the notes themselves. This is editable because literally you can pull these notes apart, you can move them around, you can change the instruments, you can do whatever you want. And then you can synthesize to get the audio, or you can have DAWs, digital audio workstations, that are the good ones. They have good sound samples, so you can have even better synthesis. You can add effects. You can do whatever you want. You can even hire musicians to play the composition. So it's very flexible, and per minute it depends on the tempo, but you have at most 5,000 tokens. So compared to 1 million samples, this is very manageable. therefore, when you use neural networks, you can have much larger context lengths because it's much smaller. So, and when I started this PhD, we didn't have diffusion models for audio, etc. And the right way to go was to go with the MIDI symbolic music representation. So then what we're doing here is we're kind of focusing on composition rather than the audio quality. So our claim is that once we have the musical composition, it's kind of straightforward to get to audio after that. So in this work, when I say music, I mean MIDI in symbolic format. So we all do machine learning. Yeah, it's the state of the art in almost everything now. If we were to have a machine learning approach to compose music based on a video, we would have this pipeline. We would have the model in between. The input would be the video, the output would be the video. And to train this model, your inputs would be video, your targets would be music. And by music, I mean MIDI. So this training data set would have to be pairs of video and MIDI. But we don't have such data sets. We have data sets that are either very specific, like music performances. What they do is they focus on the top of the piano, like a camera looks at the piano and looks at the fingers, then they can get the notes. But this is very specific. And they're usually very small. They're smaller than 1,000 samples. So this is too small to train deep neural networks. By the end of this implementation, we want flexibility, meaning that the model should work with any video, not just like specific instrument playing videos, etc. And we want musical diversity and quality, meaning that if we have a very large data set, we can achieve that, but not with 1,000 samples. And as you all know, as long as you have bigger data with bigger models, gives better results. So that's the overall approach in this research, that we want to enable the use of bigger data and we want to implement bigger models. So then, how do we utilize more data here if we don't have the paired data? What we do here is we split this process into two. So we have a video model, video analysis model, and a music generation model. And in the features that are taken from the video analysis model. So when you split this into two, you can train these individual modules using individual data sets. So here you can train it purely using video data sets, and the music generation model, you can train it purely using MIDI data sets. And here we have MIDI data sets such as LAC MIDI data set, which has 176,000 samples. So this is quite good. It's the largest MIDI data set. But now let's take a look at what these video features should be for music generation. So these are the intermediary features that we will use. The research on both musicology and also machine learning research points out that the music should match the video's emotions and the temporal dynamics. These are the two properties I've shown you in the first slide. So then we can branch out our model into two stages and two pipes. So emotion and temporal analysis, these two-stage model. So to go real quick, so the video will be analyzed in terms of emotions, and these emotions will be used to condition the music generator. And on the other branch, you do temporal analysis, and then you have some temporal features, and these will be used to condition for temporal music generation. And at this point, we have MIDI, and in order to hear, we need to convert it to audio. For this work, we just use a software called Fluid Synth. So this is like a very simple library. It has library of sounds, which is associated to every single note. So you can convert this to audio to hear it. But the result is like a computer game music from the 90s. But at least you can hear the composition. Okay, so now let's go one by one. Let's start with the emotion branch, but we have to first take a look at the emotion representations. So in order to represent emotions on computers, you have two main approaches. One of them is categorical approach, which is very simple. You can have discrete categories like happiness, sadness, anger, etc. So these are just categories. And the second approach is dimensional. So you can have continuous values. So over here on the right-hand side, you have this dimensional approach. This is a 2D plane of valence and arousal. Valence tells you how pleasant a feeling is, and arousal tells you how active it is. So if an emotion is pleasant and active, this is like joy. If it's unpleasant but active, it's anger. If it's unpleasant and passive, it's sadness. And if it's pleasant but passive, it's calmness. But these are only 4 emotions that are mapped to the quadrants. The beauty of this representation is it's continuous, so you can have any emotions, on display. So it's quite nuanced. And for example, if you have an emotion with valence 0.9 and arousal 0.2, it will be somewhere here. So this is a pleasant emotion, which is a little bit active. So it's not like super joyful, but it's a bit better than calm, and it's very pleasant. Now we can go step by step in each component in the model. So first we do emotion analysis from video. So what we would like to have is to have a model. This is a very simplified version. We have a video, input frames, and audio into a trained model, and the trained model will say this is a sad video. It will give the emotion. So here there are some challenges. The emotion labeled video data sets usually are they're also very specific, like focused on the face or focused on specific tasks like social interactions. What we want is variety. So to this end, we use user-generated videos, which is user-uploaded videos that are uploaded to YouTube and Flickr. And there are some other challenges. One, raw videos are huge. So you have individual frames and pixels, you have the audio. So when your data set is not big enough, but your input space is quite big, you have this what we call curse of dimensionality, and you see lots of overfitting. And the second problem is the multimodality. So videos are more than what the pixels are. You have scenes, you have faces, on-screen text, audio, events, speech, and music. So all of these are related to the emotion of the video. And if you were to try to exploit all these modalities using a single model, it's quite difficult. You usually fail. So the question here is, how do we ensure generalization and multimodal representation? So how do we solve these 2 problems at once? And the solution is to use pre-trained models for each of these modalities. So these pre-trained models would cover the multimodality, and they're compact because they're just features. Yeah, they're not the whole pixel space. So what we did is we found a bunch of pre-trained open source models to analyze different things. These are to evaluate the facial expressions. If you see a person in a video, to do this, we have a face detector followed by an expression classifier. You have clip features for image understanding. You have OCR models to detect the text. You have ASR, automatic speech recognition, to get the speech. And then you have audio, events, and music. And furthermore, this OCR text and ASR text can be processed using a language model. And here we choose to have a sentiment model since it's related to emotions. And what we do here is we just take their final activations. We don't take the final probabilities, of course. Just take the activation and combine it using trained modules. So they can be anything, but here we chose to use multi-head attention, cross attention, and a linear layer to get the emotion, basically. So in the end, the result looks something like this. So this is a sample input video.
We'll do it live. Okay. Do it live! I'll write it and we'll do it live!
So when we analyze this video, you can see a few things. So using the clip encodings, we can predict a caption. Here the caption says, politician gives a speech on the first day of the second term. We know it's wrong when we look at the video and listen to the speech, etc. But when you only look at the frame, which is what clip is doing, it could be right semantically. Secondly, we found the face and evaluated as angry. So that's one thing. And then we can have the OCR text within these yellow boxes. And with OCR, you can feed this into sentiment analysis. These characters don't mean much in terms of emotion, so this is neutral. In automatic speech recognition, actually what he's saying, if you don't focus on his tone, it's kind of positive. He says, we'll do it live. So it's analyzed as positive. And you have audio classification result. It's like 50-50 speech and music. And finally, emotion prediction, which is anger. So these things are for illustration. So we never use the final prediction of these intermediate models, which always take the activations so that they're rich in features. And I have a Collab app because what I saw was that there is no open source model to analyze emotions of a video. So I put one on Collab. You can go ahead and use it. And then at the end of the presentation, I give you the GitHub repositories as well. And I'm not going to go too much over the quantitative result, but it outperforms the state of the art basically. All right, now that we have the emotions, how can we use these emotions for generating music in specific emotion? So here, the simplified model would be this. We would have an emotion as input. The trained model will generate the MIDI based on that emotion. But once again, we have the problem of data. This time we emotion labeled MIDI data, which we needed at large scales. And here you can see that. So these the ones with emotion labels are quite small. The maximum duration is like 11 hours. But as I said in the beginning, we have this one MIDI data set, which is 9,000 hours. So ideally, if we could label this data set with emotions, that would be great. And this is what we try to do here. So, but then how can we do it automatically? Yeah, we don't want to go by like 9,000 hours of audio. So MIDI songs have their audio versions. So for some of those MIDIs you can find from the metadata, etc., they're audio versions. So if we can find labels from the audio modality, it would weakly match the MIDI because they're the same composition. So even though they're not exact matches, if you can have enough samples, we hope that this compensates for this noise. So, and Spotify has valence labels for audio, or it used to have, not anymore, but when I was doing it, they had. So valence, remember, it's the pleasantness, unpleasantness. So I went through a bunch of different data sets. Some of these data sets actually are like dead, but I'm hosting them on my GitHub. So you have the MIDI data set, and then it has some track IDs, which could be matched to another data set called million song data set. And then it's matched to another data set called Econest song ID. This company was bought by Spotify later on. And some of these samples have Spotify ID, so I can prompt Spotify API. But if I don't have the Spotify ID in million song dataset, I have the artist name and the song title. Not for all the songs, but for some of them. So I can use this to search the Spotify dataset. And for arousal, arousal means how active your music is. It's easier to model it. It's not as complex as pleasantness, unpleasantness. And the state of the art also does it. They model arousal using MIDI features such as tempo and note density. So if a song is fast, we can say that it's an active song. And in the gyms, when you're running, you try to have a music with high BPM. It's because it has high arousal. So they correlate quite well. So we can extract the MIDI features, which we can use to model valence and arousal. So just arousal. And the valence is taken from Spotify. And then, as a result, we found 34,000 of these songs, like valence from Spotify, and we can get the arousal. So in the end, this is 2,000 hours of MIDI. So compared to the state of the art, it's quite good. But once again, it's weak matching. And then how do we use it to condition the music generator? So we have some approaches here. The first one is no conditioning, real quick. So all these the blue dots, they are tokens of MIDI. So you can think of them as nodes. They are discrete, yeah? So what we do here, as you all know, for sequence modeling, we can put them to embedding layer, and then we can put it to a transformer model. In standard conditioning, what they do is, this is also for language models. To condition a language model, you can put some prefix, in ChatGPT, you can say like, okay, edit this, but make it super formal. So that's a condition you give to ChatGPT, which is prepended to your actual sequence. So if we were to follow the standard method, we would just discretize them into bits because these are continuous values for valence and arousal. And we will just concatenate them in sequence dimension, put them into a layer, and then put the music transformer. But then we say, okay, these are continuous values, so why discretize them? We just lose information. So we can just encode them using linear layers in their continuous form, and we can concatenate them in sequence dimension or feature dimension. So we can repeat them in sequence dimension so that, because this is we can make the claim that these are more global features. So it's not like the nodes are quite local, but the emotion condition is global. It affects the song on a global basis. So we can just repeat that and then concatenate to every single token. And so these two are our approaches. I'll play you some songs. So these are not cherry-picked samples. These are the songs we used in our paper as well. And once again, we're using a very primitive audio synthesis method called fluid synth. So the result sounds like computer game music from the 90s. So don't expect sumo level quality. But what I would like you to pay attention is the composition itself. Once you have the MIDI, using some more professional tools, you can always have better audio. And I'll fast forward with some of these songs just to show you how the song evolves. So this is for joy, when you condition the model with the emotion of joy. Speaker really doesn't help here, but let's listen to calmness, and I'll fast forward a bit because it becomes like a down tempo house song almost. Kind of evolved. Let's listen to sadness. And then finally, anger. Anger is quite difficult to express with MIDI music because it already sounds like a bit funny. So the way, if you think about music, like if you think of metal music, it has like lots of distortion and heavy drums and stuff. So you cannot represent them in MIDI. You have to change instruments, but that's not what we do here. We're just focusing on the composition. Like a drum bass. Actually, as I go forward, there's like a drum solo here. So it's quite interesting how the song evolves. All right, the quantitative results shows that actually this approach helps over the classical methods. And then actually, when you look at the next note prediction results, by seeing that it helps the negative note likelihood and accuracy, etc., even if it's a small amount, you see that these labels are meaningful. So if they were like random, then your accuracy would not improve, let's say. And we also have emotion classifier error, which is like we train another model to predict the emotion of a song from the data set. And then we see the L1 error between the input condition and the prediction of the model. So once again, our approaches are better than the state-of-the-art approaches. Okay, so now we have the emotion from video and emotion from, so we have emotion classification from video and then the emotion-based music generation. So now we can combine them, yeah, but not really, because there is a discrepancy here. So our video model outputs discrete emotions because this is what the data set I had, the data set I had, the best one was generating discrete emotion. They were labeled with discrete emotions. And the music model uses continuous emotions. So there is a clear divide here that we need to address. So we need to have a mapping from categorical emotions to dimensional emotions. And to that, actually, we can keep things basic. We can refer to old psychological studies where when they were developing all these emotional models, they also looked at how they relate to one another. So this is quite an old study. There have been new ones. This is almost like 50 years old, yeah. There have been new ones, but I went through the papers and the new ones have a lower sample size and they have a lower number of emotions. So this is still the most comprehensive study, even though it was done 50 years ago. And the beauty of this study is, so what they do here, they have some users, they have participants, and they induce some emotion and they ask them to rate their valence and arousal. And instead of just saying like, okay, angry, give me the emotion, they write scenarios that would induce the emotion of anger, like this happened and then, somebody was unfair to you, something like that. So I found that to be a better study. And in the end, what they do is they look at the means and standard deviations based on people's responses. So based on this, you can generate Gaussian distributions for every single model, every single emotion. So if our model were to generate an output like this, because it makes predictions, right? we can map these to a mixture of Gaussians. So we can have Gaussians from every single emotion, but we can scale them. We can weigh them based on the probability, output probability of the model. So this would be a mixture of Gaussians. So what you can later do is you can either sample from it or you can take the mean. So this will give you the continuous variance arousal values. Using this mapping, you can go the other way, even though we don't have to, for like expectation maximization or something like that. So if you have these values, you can kind of find the argmax emotion, the emotion which would give the maximum match for these distributions. So it's possible to go both ways, but here we just need to go one way. All right, so now let's look at the temporal branch. So here the question is which temporal features we choose. When I was showing you in the second slide, you kind of know my answer, but existing methods actually don't use that. The existing methods of video-based video generation, they use dense features such as video speed, and this could be optical flow magnitude. By dense, I mean you can get them for every single video frame, so it's quite dense. And this in turn controls the music note density. But I've seen some, samples, and I've seen some problems with this approach. Problem number one is because the features are dense, you're constantly modifying. So you constantly have a condition. And if you constantly modify the note density, this creates some problems rhythmically. You can disrupt the song's rhythm. And the second problem is in order to perceive that there's a synchronization going on as a user, you need to see big changes in video speed. Otherwise, like if these modifications are quite small, the human eye and the ear, we don't get it. So to address these problems, rather than using dense features, I chose to use sparse features, which could be the scene cuts, the timestamps of the scene cuts. So here you have a video and you have two scenes. Yeah, one of them is the kitchen and the other one is the living room. And here at this red line, you have a scene boundary. So I thought like, okay, if I have sparse features, I'm not constantly modifying the song, and we can perceive the synchronization because it's quite a big change. So since scene cut detection in videos is a solved problem, we just use FFmpeg. There's not much need for research here. And then we move on to temporal conditions. So here we just get the scene cuts as timestamps. So now we can use these timestamps as the condition of the music generator. But before we do so, let's talk a bit about MIDI representation, especially the timing, because this will be important later on. So this is a song. Let's say you have a piano here, and then these are the notes. Here these notes fit perfectly into these coarse grid, and here each grid, like each location, is a beat. So this actually fits the musical beat. Like every single note is on the beat. It's like very robotic. And if you were to have a music like this, you could tokenize it, in your transformer, like note, rest, 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 another note, rest, rest, like if you don't have any notes. So it would be quite simple. Life would be simple. But in real life, this is not how music is. Yeah, when humans play music, there are some nuances. So the notes don't exactly fit into those coarse grids, but rather they deviate from it. For example, here you have like this is the beat line, but the notes start slightly before it. So this is called expressive timing, and this is what I would like to use. And also in the mini data set that I have, you can never trust that your song will always be quantized triple down. So I want to use this, which makes things a bit complicated. And this is how you tokenize your MIDI. Let's say you have two notes here. You have a long C note and a short F note. Your tokens are, the first one is to set velocity. Velocity is the volume of a note. And then the second is to note on C4. So this tells me that I turn on this note. And then next, I have a time shift because for 640 milliseconds, nothing happens. So, but then you need to encode it. And then you have note off, C4, and then you have a tiny time shift, 24 milliseconds, and then you have another note. So the beauty of this approach is you encode the time shift in milliseconds. So this is absolute timing. So this doesn't have to be one beat or half beat or whatever. If you have a fine enough representation, and here we use 8 milliseconds, you can represent almost any time in the multiples of 8 milliseconds. And 8 milliseconds is really short, So we actually don't need anything shorter. So the beauty of this approach is you can represent music that is played by humans. So it sounds more natural, it doesn't sound robotic. So how can we use this? How can we maintain this representation while putting conditioning on top of it? And then we match video boundaries to music boundaries. Yeah, that's our goal. But what are musical boundaries? So one approach in the first slide you've seen is the melodies, the segmented melodies. But doing segmentation of this is not trivial. So we leave it for future work because really you need a data set, you need labels. We propose a simpler approach, simpler boundary at least, for a proof of concept. So what we are focusing here is we're focusing more on the conditioning way of the neural network rather than choosing which boundary. And once we have the boundary, if you were to have a musical segment boundaries, you could still use that in our approach. So what we use here, we use chords. So chords in music is multiple notes played at the same time. So here I call something called strong chords, which is guitar or piano, 3 or more simultaneous notes, lasting at least 2 beats. So here this would be a chord, and this is the boundary of the chord, so where the chord starts. So then what we are doing with video and music is they're both timestamps. So how can we match them? So we have this hybrid approach for training because we don't have videos matched with MIDIs in the first place. For training, we use purely MIDI. So we take musical boundaries and we use musical boundaries during training. At inference, we replace those boundaries with video boundaries. So it should still work. Yeah? If you train your model to just take the timestamp 8.3 and generate a chord at 8.3, at inference time, when you take the video boundary, which is like, I don't know, 7.3, it would try to create a chord at that boundary. So the result would be strong chords are generated near the scene boundaries. But still, implementation-wise, is a bit difficult. Since we're using tokens, so this is like, once again, this is like language, you know, like a transformer model. We need a special token to show the model that this is a chord. The next thing is a chord. So we define this special token, chord token. So in natural language processing, you can have special tokens like start of sentence, end of a sentence. So this is another special token. But then how do we use this to condition model? One simplistic approach would be, okay, just use it at inference time. When you have the scene cut boundary, just force the chord token and let the model generate the chord itself. But this is problematic in 2 ways. First, if you force the chord at an exact time to the milliseconds, you will disrupt the rhythm because maybe the chord doesn't fit exactly there. It can fit somewhere that's close to it, that's musically meaningful, and the human eye would still see it as matching the scene because we don't see the milliseconds, but we can hear the milliseconds if it doesn't fit into that beat. And the second problem, the notes before the chord, the preceding notes, should be suitable with the chord. So if the model has no idea it's generating the music and suddenly I say, okay, put a chord, it may not, like that chord may not match the preceding note. So it may sound very abrupt. And here, because the generation is autoregressive, the model is not looking back. Yeah, it's always looking into the future. So the solution, the model should place the chord near the scene boundary, not exactly on the scene boundary, where rhythmically appropriate. And the model should be able to anticipate, in quotes, an upcoming chord so that it generates the preceding notes accordingly. So if it has a knowledge, okay, I have a chord coming, it would change its creation of the notes before the chord. All right, so this is what we wanted roughly. But then how do we use this event-based? So this is event-based MIDI encoding. How do we maintain this and then do conditioning basically? So our answer is what we call boundary offsets. So we coined that term. So offset here is how much time I have until the next boundary. So here, when you have a scene cut or a musical boundary, way before that scene cut, your offsets are quite large because you have a lot of time until that chord. And as you get closer and closer, these offsets drop. And when it's 0, it's kind of generate the chord. But then the model can still adjust itself. So basically, this allows the model to think ahead. This allows us to signal the model. Okay, a chord is like a boundary is coming in 8 seconds, in 6.3 seconds, in 2 seconds. So it's like a countdown for the model. It's like an auxiliary input. So we can incorporate this into the model. So this is kind of a position encoding or positional information. It's not absolute position, but it's position in relation to the upcoming boundary. So, in transformers, you have positional encodings, and this can be learned. And then we have the boundary offset. So we can put them into a feed-forward layer and create encodings, and then we can concatenate them in feature dimension. So what we are doing here is we are enriching the positional encoding. So we are creating another type of positional encoding to add onto the model. And then on the upper side, you have the emotion conditioning that I talked before. And the nice thing about this is we're not touching the transformer body. So if we want to use a pre-trained transformer, this is also easy. Or if we don't want to use any boundary offsets, it still works. So there is no architectural change to the transformer. So this is, and also I did try some changes to the transformer, and I saw that it actually doesn't perform better. But this is a problem I have with the research culture is I see that in papers you see super complex models, and then I try to replicate them, and I make the model super simple, and it kind of gives you the same accuracy. So I wonder if it's like a conscious choice of researchers to overcomplicate the model so that the paper gets accepted. But anyway. So now we can bring it all together. So the model uses emotion and synchronization. So I called it MSync. So it's a reference to like a 90s band, if you're old enough. And so you have 2 branches. The one is emotion. So we have the emotion classifier, outputs discrete emotions. These discrete emotions are mapped to a mixture of Gaussians. And then we can sample from it or use the mean. So this is one branch. And the temporal branches, we have the scene detector using FFmpeg. And we do a little difference filtering because if the scenes are too close, then you're trying to generate chords that are too close, so it doesn't really sound good. And then these features are the music generator to generate the MIDI. So we evaluate this using a survey. What we do here, we have 2 other methods. We are the only 2 other open source models that takes the video, arbitrary videos, and generate MIDI. And we put them in random order, side by side, and we ask the users to rank 5 things: musical richness and diversity, independent of the video content; the musical quality, independent of video content; then how well music matches the video in terms of emotion, match in terms of rhythm and timing, and overall terms. And we use a ranking approach because you could use a 7-point Likert scale or whatever, but then you have the user bias because some users will think the music is amazing, so they would give points like 5, 6, 7, and another user would be like, this is horrible, they would give 1, 2, 3. So by having a ranking approach, we're kind of eliminating user bias to focus on the comparison between 2 models. And I use this platform called Prolific. I could employ 153 participants. It's okay, but not amazing. If you were to plan to do subjective studies, like the quality of the labeling is not the best. But we can talk about it later if you want. Okay, so I'll play you some samples, just the beginning. And then 2 videos. The first video is kind of positive overall, and the second video is a bit negative and dark. So this first model is controllable music transformer. They don't use emotion at all, and they use dance conditioning. And at this point, if you thought my musical samples, sounded horrible because of the MIDI, you will hear that the others also sound horrible because they also use MIDI. So it's a fair comparison. So, and we of course synthesize this audio using the exact same model, exact same, like fluid sync, same audio sample, etc. So let's listen just a bit. one thing you would realize is there are no drums. This could be due to the fact that they're constantly modifying the note density because it's a dense conditioning. You cannot constantly modify the drums. Yeah, you have to have a solid beat, solid groove. So the second approach is called video to music. What they do is they using a machine that they use emotions as well as dance conditioning. They generate the chords of the song, not the notes. And then they use a fixed arpeggiation pattern. By arpeggiation, I mean you have a chord with, let's say, 3 notes. So you can take these notes and then put them linearly. So this is what we call by arpeggiation. But it's a fixed rule-based method. And I'll explain you the downside of it. So the first approach. So they sound very, very similar to my ear it is. It kind of changes as the video progresses, but this is the downside of using a fixed arpeggiation pattern. So when you only generate the chord, it sounds quite similar. And also they use, another thing is this is not fully automatic. You need to input the key of the song at the first chord. And for fairness, I just put like a C major and C chord and let it generate. But then because it has the same initial conditions, it sounds quite similar across different runs. Okay, this is our approach. Once again, 2 things I would like you to pay attention to is the emotions and the steam boundaries and the chords. And the second video, I'll fast forward a bit because it sounds a bit repetitive and then it kind of changes. But then it changes at the generated chord, which is nice because this means this chord conditioning works as a regularization method, not in machine learning terms, but in musical terms. Like it avoids being overly repetitive. So this generated chord kind of changed the tone of the song, which is nice. And then results. We see so we have 5 metrics, 2 data sets. One of them is music video, so we could use them as like a pseudo ground truth for the next quantitative approach, like an objective evaluation. And across all data sets and all metrics, it outperforms the other 2 methods. And then when you look at the 95% confidence margins, and when you look especially at the matching metrics, the difference between the closest one is kind of exactly the sum of these 95% confidence margins. So here we have statistical significance. And this is the more raw results. And then you can do objective evaluation. To be honest, I did that because the reviewers asked for it. In my opinion, this shouldn't have an objective evaluation because you don't have matched data set with video and MIDI. So how can you do objective evaluation? So there are 2 things you can do, but this would be more useful for raw audio and not for MIDI, but we did it anyway. So the first one is audio video alignment, intersectional reading. We check if the audio and video peaks occur within the same window. So you check if the audio matches the video. And here we synthesize the audio already. And I checked at 2 levels. One of them, because you can check at different levels, this window size can change. One of them is super short at a video frame level, and the other one is at level of 1 second, so it's longer. So here higher is better. And the second metric, this is mostly used for audio generation models, diffusion models. It's a KI divergence. So you compare the ground truth music to generated music, and you measure the KI distance between the output probabilities of a pre-trained music classifier. So you put these audio, the ground truth, and the generated into a classifier, and you compare the probabilities to see if they match the results. So here lower is better. And our approach beats the state of the art in everything except the second level audio alignment only on the EMO-FB dataset. But even here, the difference is quite small. So basically, and then you have the open source code and datasets. So the last one, the video-based music generation, it's still not open source because we're still, doing revisions on the paper. I'll make it open source, but this is my GitHub repo, so you can go to it, and when it's updated, you will see it. But for video emotion classification, you have the collab and also the source code and emotion-based video generation. Also, pre-trained models, data sets, so everything is very well documented. And this ECMAN 6 video dataset, video emotion dataset, it kind of got lost, so I uploaded to Zenodor, so I hope it lives there. And basically that's it. So thanks for listening, thanks for inviting, and I'm ready to have your questions if you have any.
Okay, thank you so much, Serkan. I'm going to stop recording. And